Welcome back to the classroom. Today's topic is the study of a Zener diode. First one is Introduction of a Zener diode. This video is sponsored by Genreviews.online. Genreviews.online is one of the review portal site. Zener diode is a distinctive semiconductor device known for its unique operational characteristics, making it irreplaceable by any other electronic component. Its essential features fulfill a long-standing requirement in electronic circuits. Among its various functions, it serves as a constant voltage reference and voltage control element across a broad range of voltage and power levels. What sets the Zener diode apart from other semiconductor devices is that its electrical characteristics stem from a rectifying junction that operates in the reverse breakdown region. The following sections will provide a comprehensive discussion on the reverse biased rectifying junction, related terminology, and the properties that arise from it. Zener diodes are made from silicon, and specialized techniques are employed during their manufacturing to achieve the desired properties. This manual is designed to inform engineers, equipment designers, manufacturers, and experimenters about the fundamental principles, design features, applications, and benefits of this significant semiconductor device. Next is the brief study of Zener diode semiconductor theory. The active component of a Zener diode is a semiconductor PN junction. Various methods are used to create PN junctions in different types of semiconductor devices. Among these methods, alloying and diffusion are the most common techniques employed to fabricate Zener PN junctions, allowing for precise control over the Zener breakdown voltage. Currently, Zener diodes primarily use silicon to form their PN junctions. Silicon is categorized as a semiconductor because it is a poor conductor in its pure form. By adding controlled amounts of specific impurities to the semiconductor, its electrical conductivity can be improved. Depending on the type of impurity introduced, the semiconductor can exhibit either p-type or n-type conductivity. N-type conductivity in a semiconductor is similar to the conductivity resulting from the moment of free electrons in a metal. In pure silicon at room temperature, there are not enough free electrons to conduct electricity. Silicon is a tetravalent element, meaning it has 4 valence electrons in its outer shell, which are largely fixed in position due to the covalent bonds in its crystal lattice structure. When small amounts of donor impurities, such as phosphorus elements, are introduced, the pentavalent phosphorus atoms contribute additional electrons that are not intended for the covalent bonds. These impurities are referred to as donor impurities because they donate free electrons to the lattice. When an electric field is applied, these donated electrons can move from the negative to the positive side of the crystal. The term N for this type of conductivity indicates that the charge carriers are negatively charged. P-type conductivity involves charge carriers that behave as if they are positively charged. While it is known that electricity is always conducted by drifting electrons in any material, there are no positively charged carriers in solids. However, positive charge carriers can exist in gas and liquids as positive ions. In a semiconductor crystal, the positive nature of the current flow can be understood as the moment of vacancies known as holes in the covalent lattice. These holes move from the positive side toward the negative side in an electric field, acting as if they were positive carriers. P-type conductivity in semiconductors occurs when acceptor impurities, such as boron from group 3 elements, are added to the silicon crystal. Boron atoms, which have 3 valence electrons, integrate into the tetravalent silicon lattice. Because these boron atoms cannot form complete covalent bonds with only 3 electrons, they create a hole in the lattice, resulting in an electron deficiency. These holes can easily accept electrons from external source or those generated by radiation. This is why they are referred to as acceptor ions or acceptor impurities. When an external circuit is connected, electrons from the power source fill these holes from the negative side, allowing electrons to jump from one hole to another throughout the crystal. Alternatively, this can be viewed as the moment of positively charged holes towards the negative terminal. This moment of hole is what defines p-type conductivity. When regions of n-type and p-type conductivity are created next to each other within a semiconductor crystal, the resulting structure is known as a p-n junction. This is the brief study of Zener diode. Thank you for watching.